Now for the last part of the problem. We've already figured out we have a Ka for this very, very weak acid, 3.2 times 10 to the negative 8. And that's our acid, HOCl, a hypochlorous acid, where you've dumped some sodium hydroxide in it. And when you do that, you convert the hypochlorous acid into its conjugate base, the OCl. We calculated that by the time you were finished adding this sodium hydroxide, you still had some acid left, 1.67 millimoles, and you produced a good deal of its conjugate base. So now we've got more conjugate base. This is produced, adding sodium hydroxide, this amount to it, has produced a significant amount of weak base, the conjugate base, compared to the amount of acid left behind. We've got significant amounts of these two things battling for the neutrality or acidity or alkalinity of this solution. This sentence is really important. Since you have significant amounts of both the acid and its conjugate base present, this is a partial titration, and this produces a buffer solution. When you titrate a weak acid with a strong base, you will produce a buffer. Now, here you're doing your titration, you just start with some acid, but all of a sudden now you've got some conjugate base. This is a buffered solution, and then finally we wipe out all of the acid and just have our base here at the end when we have a pH of around 11, based on the concentration of the OCl, because there's no HOCl left behind. Let's answer the question. Without using a calculator, how will the pH compare to the pKa? Well, we've got to figure out the pKa. Let me pull out the calculator. By now, this should be automatic. We're going to get a p-value negative log. Thank you, Sorensen and Napier, for coming up with the logs and using it for describing acids and bases. And I'll get that 3.2. Second function times 10^2, and make that the negative 8. Oh, this is going to be close to 8. Let's enter 7.49. That is our, voila, pKa. In effect, 10 raised to the negative 7.9 produces this very, very small number. Without the calculator, how will the pH compare to the pH? Well, this is where we've got to know our Henderson-Hasselbalch. You can look it up on the equation sheet, but on a test, you got to flip forward. Then remember, this is something you're going to memorize before the AP exam. And it's not that bad. pH is equal to the pKa. I mean, that's pretty easy. pKa plus the log, and this is the tough part. You've got to remember to have the base on top and the acid on the bottom. There's another version of this where you have a negative and an acid on the top of the base, but this is the one they use on the AP exam, so we'll use it. All we've got to do is figure out our conjugate base and our conjugate acid, and we're going to be in pretty good shape for finding out what's happening. Well, now we could do the math, but we can do it without a calculator, because when the base and acid are equal, we've got a logarithm of 1, which is 0. The pH equals the pKa. And we just figured out the pKa is being 7.49. When we have an equal amount of base and an equal amount of acid, our pH will be 7.49. We're going to be moving along our titration. Now, this is our endpoint when we've used up all of our acid. Halfway there is right about here. And we're going to have a pH, it looks like a little bit more than 7. Right here, a little bit more than 7. Slightly basic. I mean, you couldn't tell the difference between this and a neutral solution unless you had yourself an expensive pH meter. This is when you have an equal amount of this conjugate acid and conjugate base. But we don't have that. We've got more base. We've got a larger number up here, and we've got a smaller number down here, which is our denominator. Now, we can start doing some thinking. With this larger amount of base, we're going to have a logarithm that is greater than 1. Logarithm of looks like close to 5. And that's going to be a positive value. 10 raised to the 0.5 will give you the result of this division. So this is going to be added to our pKa. And this makes sense. We've got more base than acid. So therefore, we're going to have a more basic solution. So I can just get my arrow and say, okay, our solution now, because we've got more base when things aren't equal, is going to be in the area of more alkaline. We've moved out to here, done our mid-titration where it's equal to the pH, but now we've added extra base. We're on our way to complete neutralization. Just add that, and this is a pretty easy calculation to figure out. If we have a lot of conjugate base, we'll have a pH that's greater than our 7.49. If we have more acid than base, we would have it down here. This would be our result. If we had the exact opposite ratio, if we had 1.64 of base, we haven't gone very far in the titration, and a lot of acid, this would be a negative 0.51, and our pH would be less than this. We'd be back down to 7. A little bit less than 7, and that's what it looks like here on this graph. You should understand the Henderson-Hasselbalch equation is a beautiful equation. It's nice to use. I love the math in it. We get the exactness that's worthy of a $10,000 pH meter, and it was developed to make things easy for people dealing with physiology and blood chemistry. It's a marvelous thing as long as you've got a good amount of acid and base. But you should understand the numbers behind this and how the Pka equals the pH when you have equal amount. It makes sense. It's one of these equations that fits everything together. If you wanted to describe what's happening in acid and base, you could write 3 or 4 pages, or you could write this equation, which I just love. Henderson, Hasselbalch, love ya. Okay, that's it.